Every measurement system has a sensitivity floor. Before a disturbance can be measured with confidence, it is necessary to understand how the system behaves when little or no physical change is present. This demonstration examines 3 experiments designed to explore the lower limits of the PASDE and DSE measurement framework. Beginning with a null-condition comparison, progressing to a 1-pixel positional shift, and concluding with a remove and return fixture test, the objective is to determine how directional instability fields emerge as increasingly meaningful physical variation is introduced into the measurement process. Null-condition baseline. The first experiment established a baseline reference floor by comparing nominally identical acquisition states. Although no intentional physical change was introduced, the measurement process still produced low-level drift energy arising from residual numerical, optical, and acquisition variability. These responses formed weak distributed instability fields but did not evolve into coherent directional structures or localized emergence regions. The experiment therefore characterizes the deterministic measurement floor of the apparatus, establishing the background level from which meaningful physical state deviations must separate before they can be considered significant. 1-pixel positional shift. The second experiment examined positional instability near the sensitivity floor of the measurement pipeline. A starry glass panel reference condition was intentionally shifted by approximately a single pixel relative to the baseline acquisition state. Under ordinary visual inspection, the positional change was nearly impossible to detect reliably with the human eye. Rapid toggled comparison sequences revealed only slight positional instability when alternating between the golden and detect states. Unlike the null-condition baseline, however, the intentionally shifted panel produced stronger and more organized directional structure. Within the PASDE and DSE framework, even extremely small spatial deviations generated measurable directional response fields. The resulting arrow matrices revealed coherent instability organization near the threshold of human perceptibility, demonstrating how directional measurement structure can emerge even when visible object-level change remains extremely weak. Remove and return repeatability. The third experiment examined acquisition repeatability under a practical remove and return scenario. A patterned wafer panel was removed from the fixture and subsequently returned to its original position before a new image was acquired. No visible positional change could be detected by direct observation, and the wafer grid structure appeared unchanged when compared with the reference image. Nevertheless, the PASDE measurement framework identified small localized disturbance regions and weak directional responses arising from subtle variations in illumination, placement, or optical state. Unlike the 1-pixel shift experiment, the resulting instability field lacked a strong, coherent directional pattern, indicating that the dominant source of variation was not geometric displacement, but minor acquisition fluctuations. This result suggests that the fixture maintained sufficient repeatability to preserve the underlying measurement geometry while still revealing the practical effects of real-world reacquisition. Summary. Together, these 3 experiments establish an important foundation for measurement-centered inspection. The null-condition experiment characterizes the baseline response floor. The 1-pixel shift experiment demonstrates that PASDE can measure spatial variation near the limits of human perception. The remove and return experiment shows that practical reacquisition can be performed without generating large-scale false disturbances. Across all 3 demonstrations, instability fields were extracted relative to governed reference states, persistence and coherence were evaluated deterministically, and symbolic field representations were generated from measured physical variation rather than probabilistic object inference alone. For Phocoustic, the objective is not simply detecting whether an object is present or absent. The objective is determining whether the physical state of a system has changed, quantifying that change, and understanding where meaningful variation begins to emerge from the background measurement floor.